Okay, our last presenter, Dr. Husham Almansour. He is a senior research officer at the National Research Council, Canada, in Ottawa. He is leading the research in the area of climate adaptation, bridge infrastructure, and protection against extreme loads. He is an adjunct professor at the University of Ottawa and also at University of Toronto. He is a member of several CSA and AC committees. Dr. Husham.
Okay, so this research actually project was phase one of a bigger project, which is now start back in phase two. And the major objective of this project is actually to develop protection systems and to understand the mechanics of damage under extreme loads, which in this case blast and impact loads, as compared to quasi-static. I have to admire the work of my colleagues. This research was done with, jointly with the University of Ottawa, Professor Marasa Choglo and Professor Palermo, who moved to York University actually now, the part which is related to the impact. I will go over a short introduction and then I will discuss the blast versus the quasi-static and the impact versus quasi-static in sense of damage mechanism and also the behavior of the column, because we investigate columns here, and the final conclusions. So here, of course, there's a growing concern about the man-made hazards in sense of blast attack and sometimes high-speed impact, which resulted in debris or due to the blast itself or ballistic attack. And of course, there's need to mitigate the risk of failure of and the successive failure of building due to this kind of extreme loads, and then to investigate actually the capability of the advanced composites. And the focus here is on CFRP, as you will see, is part of bigger project. The other part, unfortunately, is classified, so where very advanced materials was used in next stage of protection to provide extreme protection for some important facilities. But this is focus and open, the open information part of the project. The need to evaluate actually the impact and advance of advanced composite on the damage mechanism. So what is the difference when we are using the advanced composites? And this is an example of severe damage in a building. Actually, when the explosion is very close to the building, so although it considered as nearby explosion, this type of explosion around 10 feet from 10 to 15 feet from the face of the building. But in general, when in this study, actually, we discuss both the far field, which, as you can see, the far field explosion, when the explosion is around more than 100 or more feet from the targeted building. So the formation of a full blast shock is actually can be seen in those, but also actually the magnitude and the sequence of the loading due to the reflection, especially in the urban environment, could result with multiple attacks to the buildings, actually, rather than only the single that we can simulate in the lab. So here is an example of the mechanism of the failure. As you can see, as the blast wave is progressing and developing within very short time, we have in the first picture at top in one. Actually, the blast wave is just reach the surface or the exterior envelope of the building, and then a sudden damage to the exterior envelope could happen, and because of that, there is a massive uplift pressure applying almost tensile stresses on the columns, while of course we are designing the columns on for compressive force. And after that, as the the bulk of the pressure is exceeding the building, there is a back force pressure and up to down pressure generated with the evolution of the wave, and then we will have back massive compressive pressure applied on the columns. So the columns at the beginning are facing lateral pressure, then tensile pressure, then sudden compressive pressure when, of course, depending on the size of the explosion itself. So as a result of that, as you can see, different local damage could lead to a progressive redistribution of the forces in the building, and then a progressive collapse could happen. Now, the progressive collapse can be very severe or can be localized, as it depends on the design of the building itself. Now, in other cases, in other environments, when the reflection is really a big issue in the explosion, similar to explosion below a bridge, so the reflection can actually magnify the blast pressure and extend the period of the pressure by up to 3 times, as observed by several researchers. So here the major objective is to investigate the effect of blast and hard surface impact load on the structure performance and the damage and failure mechanisms of reinforced concrete columns, and also to investigate the stage of damage, the load deformations, and so on, as structural performance parameters. And this, the experimental part of this study, actually, we have a column up, the size is 6 by 6 inch, 150 by 150 millimeter in section, and the height is around 2.4 meter, and we selected a boundary condition of a pin ruler here in the lateral direction, while we're applying an axial load up to 40% of the full capacity of the column. And we monitor actually the lateral reaction and also the axial, the change in the axial force during the test. We use very advanced monitoring technologies where we are monitoring actually up to 1 million data point per second per channel. And also we monitor the strain wave inside the steel and on the surface of the concrete, and in between the surface of the concrete and the FRP, which is not shown really in detail here because of the short time. So we have several, for the blast test, we have around a total of 32 columns tested in 2 different matrices. The matrix 1 is to explore the effect of actually axial load versus no axial load. So the second matrix is actually to explore the effect of the FRP of different orientations. So we have the laminate form from different layup and different orientation of the fibers. Actually the FRP is, we use CFRP and epoxy resin in this case. And here are details about what type of orientation and also how many specimens per for each test, and I will show you a sample of the results. We used University of Ottawa shock tube And here is a simplification of the system, actually a sketch showing the lateral load measurements in top and bottom, and also we use laser devices to see the deformation and high-speed cameras to monitor the test itself. And actually we analyze all the strain and the strain waves throughout the formation of the plastic hinge and so on. So here is a sample of the results, and as you can see with the FRP, the deformation or the residual deformation is very low, while without FRP actually the residual deformation is extremely high. And in this test actually we use only single shoot, not multiple shoots. So it's just one single shoot which result in failure. Here is more examples about different types of FRP and how they are actually the failure, how is developed. This is the deformation time history of some specimens, and I will show you, here is actually the resistance function of, I did not mention that some of the columns are really designed according to 1963 code for non-seismic columns, because the major objective is to investigate the strengthening of existing buildings, and some of the columns are designed for seismic designs, and then the comparison, of course, between different FRP orientation. And as you can see, some orientations gives extremely high response, and then it's bounced back to its original with very high energy absorption. And here with the seismic, we have better performance, of course, and the FRP is also modified with the seismic versus non-seismic to fit the behavior of the column and what is predicted to be the best behavior. And as you can see, the energy is increased, which is the area inside the the overall cycle of the loading. Here is an example of the damage, and when we are using plus minus 45 FRP, as you can see, the damage is really changed, and I will show you some experiment and test videos, some videos of the test, and which shows how the damage is changed with the FRP orientation. The residual, actually the post-blast capacity after the test, and while those columns are really bounced back to its original position with minimum lateral residual deformation, we load them axially up to failure, and as you can see, some of them actually gives almost the same strength as the design strength. So some of them gives more when we are using the plus minus 45 and extra 0.90 FRP. So it gives much better behavior than the expected. And this to actually maintain higher capacity after the real blast shock when the pressure phase comes, as I explained in the beginning. So here is some videos. I don't know if I can, how to run the video from the, should be the mouse. Once, how to
So
click
if you
on,
click,
click
that
on
should
it, and then,
is working?
yeah, it's working now. And then I want to click to the second one.
You just click
Ah,
on
okay.
system.
Okay. So here is a non-protected column. As you can see, the damage is massive, and actually this is just a sample. Some samples develop very large deformation, larger than what you can see here. And this is the second test. I don't know if it is working. Yeah, it's working now. And you can see this is with the FRP. So the column is just bounced back. And actually, just to mention, the total shock is the extreme capacity of the shock tube with the FRP, while it's almost half of the capacity of the shock tube without the. So for the quasi-static, actually, we developed a system that can simulate the uniform distributed load while simulating the blast, but in very slow application. And it can maintain very high deformation. At the same time, we have a full application of the axial load and full monitoring of the reactions. So similar to the setup for the shock, but in the shock tube, but now we are using actually quasi-static testing in our labs, and we compare the result is exactly the same type of FRP, the same type of setup, and we compare it with the blast. And as you can see, the load deformation from the quasi-static test is shown here, and actually here is the development of the deformation throughout the up to the full failure with over the length of the column. Here is a video which show you the differences in the failure modes. As you can see, here is 090, here 090 plus minus 45, and as you can see, the failure of the FRP is totally different. And here is woven 090, so it's again 090 but woven, and as you can see, the failure of the FRP is totally different from, in the slow motion we can see it better than in the shock tube. So, in the impact test, what we did, actually, we did exactly the same boundary. We have also lateral pin ruler, and we apply axial load in the same level, but then we apply impact force at the mid-height of the column using a special device where we accelerate, actually, pre-accelerate a mass, and then we have a hard surface that impact the, the mid-height of the column, and we actually change the distribution of the strain gauges inside to maintain a good monitoring of the strain wave as migrate through the column, and we monitor actually the reactions, the axial load, and also we monitor the cracks using high-speed camera. And this is a comparison between the quasi-static. In the quasi-static, actually, we use the same setup, but and the same surface, exactly, the circular or cylindrical surface that we apply the impact load with. We simulate it in the quasi-static, but now we're applying the load very slowly, and we compare based on the level of deformation in each case and how the damage is developed. And you can see in the impact a shear plug is formed in the top picture, and then in the lower actually is regular flexure under point load. We have, I think, video here which show how the damage is. The left is the quasi-static. The right picture is the impact. And you see with the impact we have the actually the accelerometer left the specimen because of the big shock, and then you can see the shear plug is fully formed. And I have to mention that in the reaction we have a negative reaction developed in the two reactions, But also we monitor the shock, the strain wave in the reinforcement, which actually start from the center of the impact toward the supports. And of course, we study different type of impacts, different speeds of impacts, different mass, and so on. So the observations here, actually, when we are using the CFRP jacketing, of course, the improvement or significant improvement in the strength and deformability is observed, but it's different between different layup and the other. The base layup, when we are using actually zero, the zero is in the direction of the column, the main direction of the column. The 90 is the lateral direction. And when we are using a plus minus 45, the ductility is improved a lot together. And then actually we study different percentages between those three type layers and different location of the layup and so on. And we conclude with one of the optimum distribution. Now, we call each one laminate, and then we name laminate by numbers. And the highest strength actually is when we are using 0.90, but the failure is non-ductile. But with the one with the plus minus 45 and 0.90, we have a compromisation between the strength and the ductility, and also the failure mode is highly controlled. Now, the woven, if we are using only the woven, it generates a sudden failure, actually, and more brittle failure. However, it's improved the strength at the beginning. Actually, I did not show you, we used also other types of fibers other than the CFRP, but we found that the CFRP is the base to give the highest protection. And then I will go forward for the quasi-static. In the quasi-static, actually, the failure mode is very similar to the blast failure. When you are applying very high speed load, or you are applying uniform distributed load, in the case of the shock tube, and when you are using the quasi-static mode of loading, they give exactly the same failure. However, actually the impact, the effect of the high strain rate is when you calculate it as compared to, for example, the U.S. Army standards or different standards for design for blast. Actually, it gives a lot of sense to use the amplification factors and for the material and the level of strain rate that we are using. Now, using woven plus minus 45 improve, of course, the ductility, and actually we developed a new calculation for the plastic hinge when it's used with single degrees of freedom simplified analysis model. Parallel to that, actually this is summarized the blast test. And in the blast test, actually, we compare again the different layup, and we found that some layup, which I mentioned, the 0.90 plus minus 45, gives the best behavior in sense of and the highest energy absorption, the better ductile behavior, etc. Now, the single degrees of freedom actually was used parallel to advanced modeling as well, because we used advanced modeling with the softwares we develop or LS-DYNA, but those are mainly for actually parametric study on bigger structure where we calibrate them with the test results, and then we are actually expanding the study on the progressive collapse, etc., for the full-scale structures. Okay, so I think with this, there are lots of findings, and actually 3 theses are online available, 2 master theses and 1 PhD thesis for Aus Hasek, the quasi-static, and Paul and Poe for the impact, and Bassam Kadam for the blast, where all the results, actually, the detailed results, the detailed work is fully explained and presented. Okay, thank you.